Good evening, Professor David de los Reyes. My topic tonight will be the derivation again of the formula for taking the volume of a sphere by using the last time around we used horizontal slice. Tonight we will be using vertical slice. So what does it mean? The significance of this the topic tonight will be is that whatever will be the solution, whether it will be using horizontal or vertical slice, the derived formula will be the same. That's the importance of the topic for tonight. Okay, let's proceed. Lesson number 64 on my topic integral calculus on my channel, volume, using circular disk method. We are still on the topic circular disk method. So actually, I am giving you example problems which are more popular to you guys, like the volume of a sphere, you know. So at least you know what will be the significance of the so-called integration in the so-called derivation. I will read the problem. Derive the volume of a sphere with radius r. Meaning, we will derive the formula for taking the volume of a sphere as a function of its radius. A sphere, it got only one dimension. It should be the radius or the diameter. Diameter is twice the radius. Okay, so you could actually bring out your answer in terms of the diameter, but you must have to convert it to radius since the problem is asking for the volume as a function of radius. Okay, let's bring out the figure. Y-axis, x-axis, this will be a circle, and the equation of the circle here will be x squared plus y squared equal to r squared. That's analytic geometry. So from this view here, I draw a circle, okay, so that's the view. It's just like a plane area. So if I will now try to draw a vertical slice, our solution for tonight will be by using vertical slice. The last time around, it is the horizontal slice. Okay? So I will bring out again the formula by using the vertical slice, and it is supposed to be the same. Okay? This is the differential area. This differential area here moves from this point here up to this, okay, to cover up one half of the sphere as we rotate it, right? You start from here, you rotate it till it reaches this point here. And this point is actually with the coordinates r and 0. The abscissa is the radius of the sphere and the ordinate is 0. On this point, it will be the reverse. X will be 0 and the ordinate will be the radius. Okay, we use vertical slice. So this height here is actually the variable radius. As the differential area moves from 0 to r, this height here is varying. Okay, so you cannot just use plain multiplication in the computation of the so-called volume. We should use integration. Okay, I will try to bring out one slice. One slice of this one rotated along the x-axis. Because we are using a vertical slice, right? So it will be rotated along the x-axis. Okay, this is one complete revolution. This is the thickness. The thickness is actually dx. Dx. It is along the x-axis, so it should be dx. Dx. And this is the variable radius r. I just draw one circular disc and I refer to the radius to be simply r. Okay, let's bring out the solution. Differential volume is differential area times thickness. the volume of the circular disc. Our topic is circular disc method, okay? The volume of the circular disc will be the area of the circle here, okay, times the thickness. That's volume. So actually, differential volume is differential area times thickness. From that configuration, the area of the circle is pi, radius quantity square, per circle. Thickness is dx. And again, from figure number 1, the radius is, this variable radius is actually y higher minus y lower. As this differential area moves from 0 to r, y higher minus y lower is actually varying. It is not in constant magnitude. So I place it here, y higher minus y lower. Okay. Pi times the quantity y higher minus y lower quantity square times dx. Okay, these are y's, right? So we also have to get the relation of these y's here, y higher and y lower, as a function of x. Okay? Y higher is actually the equation of the circle. X square plus y square is equal to r square. It is the equation of a circle with center at 0, 0 and the radius is r. Okay, so I will bring out that one. I will solve for y square. Y square will be r square minus x square. Then take the square root of both sides. To compute for y higher without the power 2. So these two here cancel with this. So y now, no more 2, right? It cancels out. But I will now try to place the proper subscript. Y higher. I now refer this y here to be y higher, equal to r square minus x square raised to the 1/2 is just a square root of r square minus x square. It is a circle. Okay? And what is y lower? Y lower is this one. It is this. As dx moves from 0 to r, okay, that will be the path of y lower. And as you can see it is a horizontal line. And what is the equation of a horizontal line? That coincides with the x-axis. Y lower is equal to 0. Straight line. Okay? So, we now derive y higher and y lower as a function of x. Okay, we bring back to the formula for taking the volume. So this will now be differential volume equal to pi. Y higher is the square root of r square minus x square minus 0 quantity square times dx. But this is now 0. Okay. The square root of r square minus x square raised, the square root, raise that again to the second power, the radical sign will disappear. It is just something like this, guys. I expedite a little bit. R square minus x square raised to the 1/2. Okay? Raise that again to the second power. So these two here cancel with this. So no more square root. So what comes out will be differential volume equal to pi times the quantity r square minus x square times dx. And we are now ready to integrate. Okay, integrate. But try to look back on the figure. Our lower limit is 0 and our upper limit is r. We are referring to dx. Dx is actually moving from 0 to r. Okay, so the lower limit will be 0, the upper limit will be r. So as it moves from 0 to r, then you try to complete one complete revolution along the x-axis. You are only taking 1/2 of the volume. Okay? So the total volume will be, we multiply it by 2, differential volume over 2, okay? This should be with the integral from 0 to r. we are only taking 1/2, but to compute for the total volume, we transfer this to here to the right side. So this is now the integral of differential volume equal to 2 pi. I put this 2 on the right, or just multiply all terms by 2. Left hand side times 2, cancel with this. The integral of differential volume equal to, I bring out automatic pi, it is constant 2 pi. The integral from 0 to r of r square minus x square, close quantity dx. Proceeding with the integration is 2 pi. R square is constant. The integral of r square times dx is equal to r square x. Right? Second one, it's the power formula, where the value of u is x and du is equal to dx. It is exact, so it falls under the power formula. Okay, we are now through with the evaluation of integration, so this should be a simple process for you guys. Okay, 2 pi, we place down the upper limit. R square times r will be r cube. We replace x by r now, this will be r cube over 3, close quantity. I will repeat the 2 pi, close open quantity. If x is 0, r squared times 0 will be 0, so this is 0. If x is 0 on the x cube, 0 to the third power is 0. 0 over 3 is still 0, so this is minus 0. Actually, the lower limit has nothing to do with the final answer. Okay? So what will come out? R cube minus 1/3 r cube is 2/3 r cube. R cube is actually 3/3 r cube. Okay? Because 3 over 3 is 1. 3 minus 1 is 2 over 3 r cube. So the final formula for taking the volume of a sphere as a function of the radius, volume now will be 2 times 2 is 4 over 3 pi r cube. Okay, that's the final answer. So the significance of the solution for tonight, guys, is that if by using vertical slice, the derived volume will still be the same as a function of the radius. That's the significance of that. So whatever will be the solution on your exam, you could either use horizontal or vertical slice. The volume as a function of the radius will still be the same. Okay. Good evening, Los Angeles.